Hello everyone. Welcome to Module 3 of MAT201 Partial Differential Equations and Complex Analysis. In this lecture, we will look at functions of complex variables, their limit, continuity, derivative, and the definition of analytic functions. So first of all, what is a complex function? Let S be a set of complex numbers. A complex function on S is a rule that assigns to every Z in S a complex number W, which we call the value of F at Z. We write this as W equals F of Z. So for example, F of Z equal to Z square plus 3Z is a complex function. This F of Z is defined for all complex numbers. So the domain of this function is the entire complex plane C. Now let's take another function W equal to 1 by Z. 1 by Z is not defined for Z equal to 0. So this is a complex function with domain the entire complex plane minus the point 0. Let's look at a property of complex functions. Let's say we have a function f of z. F of z is a complex number w, which we can write as u plus iv, where u and v are real numbers. Then as z is equal to x plus iy, z depends on x and y. So the real numbers u and v should also depend on x and y. So we can write u as a two-variable function u of xy and v as another two-variable function v of xy. So every complex function can be written as f of z equal to u of xy plus I v of xy. For example, f of z equal to z square plus 3z. Z is x plus iy. So we can write this as x plus iy the whole square plus 3 times x plus iy. Now if we expand x plus iy the whole square, this will become f of z equal to x square minus y square plus I times 2xy plus 3x plus I times 3y. We can combine the real terms and the imaginary terms to get f of z equal to x square minus y square plus 3x plus I times 2xy plus 3y. So for this function f, u of xy is x square minus y square plus 3x. v of xy is 2xy plus 3y. Now we look at limit in the complex case. A function f of z is said to have limit L as z approaches z0 if f is defined in a neighborhood of z0, and for every real epsilon greater than 0, we can find delta greater than 0 such that modulus of f of z minus L is less than epsilon in modulus of z minus z0 less than delta. If the limit exists, we write it as limit z tends to z0 f of z equal to L. Let's compare the limit in the real case and the limit in the complex case. If we were looking at a real function f of x and we wanted to find the limit at a point x0, we could approach x0 only in two ways, either from the negative direction or from the positive direction. But in the complex case, z can approach z0 in infinitely many different ways. So for the limit to exist, it should be independent of path. So if this is the point z0, z can approach z0 from the negative direction at an angle along a straight line, along some curve. So there are infinitely many possible paths along which z can approach z0. Irrespective of this path, we should get the same limit. Only then can we say that the limit exists. So where in the real case, the limit could be approached in only two ways. In the complex case, we can approach a point z0 in the complex plane along infinitely many different ways. Continuity in the complex case is quite similar to the definition of continuity in the real case. A function f of z is said to be continuous at z equal to z0 if f of z0 is defined and limit z tends to z0 f of z is equal to f of 0. If the value of the function at a point is equal to the limit of the function at that point, then the function is continuous at the point. A function f is continuous in a domain if it is continuous at each point in the domain. Let's look at an example. Is the function f of z defined as z divided by z conjugate when z is not equal to 0 and 0 when z equal to 0, continuous at z equal to 0. So f of 0 is 0. If limit z tends to 0, f of z is also equal to 0, then we can say that f of z is continuous. So let's evaluate that limit. Limit z tends to 0, f of z is the same as limit x plus iy tends to 0, x plus iy divided by x minus iy. Let's approach the limit along the straight line y equal to mx. This is the straight line passing through 0 with slope equal to m. Since y is equal to mx, the limit becomes limit x tends to 0, x plus I mx by x minus I mx. We can cancel out an x from the numerator and the denominator so that this becomes limit x tends to 0, 1 plus im divided by 1 minus im. Letting x tends to 0, the limit is this complex number 1 plus im by 1 minus im. But look at this number, it depends on the slope m, which could be variable. So depending on the angle at which we approach this limit, depending on the value of the slope m, the value of the limit changes. This means that for different paths, the value of the limit does not stay the same. Therefore, this limit does not exist. So we can say that this f of z is not continuous at z equal to 0. Now we look at the derivative of a complex function. The derivative of a complex function f at a point z0 is written f dash of z0. It is defined as f dash of z0 equal to limit z tends to z0 f of z minus f of z0 divided by z minus z0. If we let z minus z0 be delta z, this definition can be rewritten as limit delta z tends to 0, f of z plus delta z minus f of z divided by delta z. Let's look at an example. F of z equal to z square is differentiable for all z and has derivative f dash z equal to 2z. Let's apply the definition of derivative to this problem. F dash of z will be limit delta z tends to 0, z plus delta z the whole square minus z square divided by delta z. This is after substituting the definition of the function f of z. Let's expand the numerator. Then we will get f dash z equal to limit delta z tends to 0, z square plus 2z delta z plus delta z square minus z square divided by delta z. We can cancel out z square in the numerator. Then dividing throughout by delta z, this becomes limit delta z tends to 0, 2z plus delta z. Now if we apply the limit delta z tends to 0, f dash z becomes just 2z. This calculation did not depend on the value of z. So for all z, f of z is differentiable and it has derivative 2z. Now let's look at a non-example. F of z equal to z conjugate is not differentiable. Again, let's write down the expression from the derivative. F of z plus delta z minus f of z divided by delta z. Our function f of z is z conjugate. So this is z plus delta z the whole conjugate minus z conjugate divided by delta z. If we apply properties of complex numbers, this is z conjugate plus delta z conjugate minus z conjugate divided by delta z. Z conjugate can be cancelled out and then our limit becomes delta z conjugate divided by delta z. If we let delta z be delta x plus I delta y, then delta z conjugate is delta x minus I delta y. Now let delta z approach 0 along y equal to mx. If this function is differentiable, this limit should have the same value independent of the value of m. So letting limit delta z tends to 0 along y equal to mx, we get limit delta x tends to 0, delta x minus im delta x divided by delta x plus im delta x. Again, we can cancel out delta x from the numerator and the denominator and we are left with 1 minus im divided by 1 plus im. Again, when we approach the limit along the line y equal to mx, the value of the limit depends on the slope m. So in this case also, the limit is dependent on the path taken. Therefore, the limit does not exist. So we can say that the derivative does not exist. F of z equal to z conjugate is not differentiable. Finally, we look at the definition of analytic functions. A function f of z is said to be analytic or holomorphic in a domain D if f of z is defined and differentiable at all points of D. F of z is said to be analytic at a point z equal to z0 in D if f of z is analytic in a small open disk containing z0. F of z cannot be defined and differentiable at just one point. For f to be analytic, it has to be defined and differentiable in a set. Now let's look at some examples. First of all, non-negative integer powers of z. Functions of the form 1, z, z square, z cube and so on are all analytic in the entire complex plane. These functions are defined and differentiable everywhere in the complex plane. The other example are polynomial functions. Functions of the form f of z equal to c0 plus c1z plus c2z square plus etc. plus cn z raised to n, where c0, c1 and cn are complex constants. These functions are also defined everywhere on the complex plane and they are differentiable. So these functions are also analytic.